Welcome. Today we are diving into a vital topic in AP Statistics. Topic 3.10. We are going to learn how to construct and interpret a confidence interval for the difference between two population proportions. By the end of this lesson, you will be able to identify the correct procedure, verify the necessary conditions, and calculate the interval and its margin of error from scratch. When we compare two groups, say the proportion of students who prefer online homework in School A versus School B, we aren't just looking at one number. We are looking at the difference between two populations. The specific procedure we use for this is called a two-sample z-interval for a difference between population proportions. Our goal is to estimate the true difference, which we denote as P1 minus P2. It is crucial when defining these parameters that you refer to the response variable and the specific populations in context. For example, P1 might be the true proportion of all adults in the US who exercise daily, and P2 would be the true proportion of all adults in Canada who do the same. Before we can start crunching numbers, we must ensure our data meets certain criteria. If these conditions aren't met, our interval might be misleading or flat out wrong. There are three main conditions we need to check. First is the randomization condition. The data should be collected using two independent random samples. Alternatively, if we are looking at an experiment, the subjects must have been randomly assigned to the two treatment groups. This ensures that our samples are representative of the populations we're studying. Second is the 10% condition. When we are sampling without replacement, the size of each sample, N1 and N2, must be less than or equal to 10% of their respective population sizes, capital N1 and capital N2. Keep in mind, if the data comes from a randomized experiment where no sampling from a large population occurred, you can skip this specific check. Third is the normality condition, often called the large counts condition. We need to verify that we have enough successes and failures in both samples to assume the sampling distribution of the difference in proportions is approximately normal. Specifically, the number of observed successes and the number of observed failures for both groups must all be at least 10. If all three of these, random, 10%, and large counts, are satisfied, we have the green light to proceed with our calculation. Now that we have verified our conditions, let's look at the building blocks of our confidence interval. To understand the precision of our estimate, we first need to calculate the standard error. The standard error for the difference between two proportions tells us how much we expect the difference in sample proportions to vary from the true difference in population proportions due to random sampling. We start with our point estimate, which is simply the difference we observed in our samples, p-1 minus p-2. To find the margin of error, we take a critical value, called z-star, and multiply it by that standard error. The z-star value is determined by our desired confidence level, for example, 95%. Think of the standard error as the typical distance our estimate is from the truth, and the margin of error as the maximum distance we expect it to be, based on our chosen level of confidence. When we put it all together, the interval is the point estimate plus or minus the margin of error. This range gives us a set of plausible values for the true difference between the two populations. Let's walk through a comprehensive example. Suppose a researcher wants to compare the proportion of teenagers who use a specific social media app in two different cities, City A and City B. In City A, a random sample of 100 teenagers is taken, and 70 say they use the app. In City B, a separate random sample of 120 teenagers is taken, and 60 say they use the app. Our goal is to construct a 95% confidence interval for the difference in the true proportions of teenagers using the app in these two cities. First, we define our parameters. Let P1 be the true proportion of all teenagers in City A who use the app, and P2 be the true proportion of all teenagers in City B who use the app. We are estimating P1 minus P2. Now we must check the conditions. 1. Random. The problem states both are random samples. We will assume they are independent of each other. 2. 10%. It is very likely that there are more than 1,000 teenagers in City A and more than 1,200 in City B. So, the 10% condition is met. 3. Large counts. In City A, we have 70 successes and 30 failures. In City B, we have 60 successes and 60 failures. Since all these values are at least 10, the normality condition is satisfied. We are ready to calculate. Now that we've cleared the conditions, let's get to the math. First, we need our sample proportions, which we call p-hat. For City A, p-1 is 70 out of 100, which is 0.70. For City B, p-2 is 60 out of 120, which is 0.50. Our point estimate for the difference is 0.70 minus 0.50, giving us 0.20. This tells us that in our samples, there is a 20% difference in app usage. Next, we need the critical value z-star for a 95% confidence level. You might remember from our work with the normal distribution that for 95% confidence, z-star is approximately 1.96. Now we calculate the standard error. We take 0.7 times 0.3 divided by 100 and add that to 0.5 times 0.5 divided by 120. Doing the arithmetic, this comes out to approximately 0.0647. Finally, the margin of error is our z-star of 1.96 times our standard error. This equals approximately 0.1268. Subtracting and adding this to our point estimate of 0.20, we get an interval from 0.0732 to 0.3268. We are 95% confident that the true difference in the proportion of teenagers using the app between City A and City B is between 7.3% and 32.7%. Since the entire interval is positive, this suggests that the proportion in City A is likely higher than in City B. Now, let's look at how this process changes slightly when we deal with a randomized experiment instead of an observational study. Suppose a medical researcher wants to compare two different treatments for a skin condition. 50 patients are randomly assigned to use a new treatment cream, and another 50 are randomly assigned to a placebo cream. After 2 weeks, 35 patients in the treatment group showed improvement, while only 20 in the placebo group showed improvement. Let's check our conditions for this experimental context. First, random. Here, we don't have random samples from a population. Instead, we have random assignment of subjects to treatments. This satisfies the randomization condition for experiments and allows us to make cause and effect conclusions. Second, the 10% condition. Because this is an experiment where we aren't sampling from a large population, the 10% condition is actually not required. We are interested in the effect of the treatments on these specific subjects. Third, large counts. We have 35 successes and 15 failures in the treatment group, and 20 successes and 30 failures in the placebo group. All counts are 10 or greater, so we can use the normal approximation. Let's go for a higher level of confidence this time, 99%. Our p-hat values are 0.70 and 0.40. The point estimate for the difference is 0.30. For 99% confidence, our z-star critical value is approximately 2.576. The standard error is the square root of 0.7 times 0.3 over 50 plus 0.4 times 0.6 over 50. This calculates to approximately 0.0949. The margin of error is 2.576 times 0.0949, which is approximately 0.2445. Our final interval is 0.0555 to 0.5445. We are 99% confident that the true difference in the proportion of patients who show improvement using the treatment versus the placebo is between about 5.6% and 54.5%. Because the entire interval is above zero, we have strong evidence that the treatment is more effective than the placebo. Now that we have mastered the calculations, it is important to understand the levers we can pull to change the width of our confidence interval. In statistics, we usually want a narrower interval because it provides a more precise estimate of the true difference. Look closely at the formula for the margin of error. There are two main ways to make this number smaller. First, we can increase the sample sizes, n1 and n2. Since these values are in the denominator of the fraction under the square root, as n increases, the standard error decreases. Think of it this way. More data leads to less uncertainty. If we sampled 1,000 people per group instead of 50, our estimate would be much more stable, and our plus or minus range would shrink significantly. Second, we can change the confidence level, which changes the critical value, z-star. If we are willing to be less confident, say, dropping from 99% to 90%, our z-star value gets smaller. A smaller multiplier results in a smaller margin of error and a narrower interval. This reveals the fundamental trade-off in statistics. To get a more precise window, you either need to do more work by collecting a larger sample, or you have to accept a lower level of certainty that your window actually contains the true parameter. By understanding these relationships, you can now explain exactly why one margin of error might be larger than another, which is a key skill for the AP exam. Before we move on to another example, let's pause to address some common pitfalls students encounter with two-sample z intervals. Understanding these now will save you a lot of headache later. The first mistake is confusing the sample proportion, p hat, with the true population proportion, p. Remember, p hat is what we calculate from our data. It's known. P is the unknown value we are trying to estimate. We check the normality condition using p hat because we don't know the true p. A second common error is ignoring the independence between the two samples. For this procedure to be valid, the two groups must be independent of one another. For example, if you were comparing the opinions of husbands versus the opinions of their wives, those two groups are not independent. In that case, you couldn't use a two-sample z-interval. You'd need a different procedure for paired data. Finally, be careful with your interpretation. We are 95% confident that the true difference is in our interval. This is correct. Incorrect is saying, there is a 95% chance that the difference is. A confidence interval doesn't tell us the probability that the true difference is in a specific range. Once the interval is calculated, the true difference is either in it or it isn't. The 95% confidence refers to the method. It means if we took many samples and built an interval from each, about 95% of those intervals would successfully capture the true difference between the populations. If an interval for p1 minus p2 is 0.02 to 0.08, does it suggest a difference? Yes, because 0 is not in the interval. One more tip. If your interval for the difference between two proportions contains 0, it means that no difference is a plausible value. If the entire interval is positive, like 0.02 to 0.08, then we have evidence that p1 is likely greater than p2. If the entire interval is negative, p2 is likely the larger one. Let's try another full example to solidify these steps. Imagine a survey is conducted to see if there is a difference in the proportion of people who support a new environmental law in two different states, State X and State Y. In State X, 220 out of 400 people surveyed support the law. In State Y, 300 out of 500 people support it. Let's construct a 90% confidence interval for the difference in proportions. The conditions are all met. We assume independent random samples, the 10% condition is likely true for both states, and the large counts condition holds with at least 10 successes and failures in each group. Now, let's find our point estimate. The difference in our sample proportions is negative 0.05. This means in our samples, State Y had a higher proportion of support than State X. For a 90% confidence level, we use a z-star of 1.645. Our standard error is calculated using the sample proportions and sizes, and comes out to approximately 0.0331. Multiplying our critical value by the standard error gives us a margin of error of 0.0545. Our final interval ranges from negative 0.1045 to positive 0.0045. Notice that 0 is included in this interval. Because 0 is a plausible value for the difference, we do not have convincing evidence that there is a true difference in support for the law between the two states at the 90% confidence level. Even though State Y looked higher in our sample, the difference was small enough that it could have just been due to sampling variability. We have spent a lot of time on the formulas, but on the AP exam, you are often asked to explain the meaning of these numbers in context. Let's look deeper at the standard error. In our previous example, we calculated a standard error of 0.0331. What does that actually mean? If we were to repeat this survey process many times, the difference in sample proportions, p hat 1 minus p hat 2, would vary from sample to sample. The standard error of 0.0331 is the estimated standard deviation of that difference. In simpler terms, it is the typical amount that the observed difference in proportions will vary from the true difference in population proportions. The margin of error of 0.0545 tells us that based on our sample, we expect the true difference in proportions to be within about 5.5% of our observed difference of negative 5%. Take a moment to think. If we needed to be more precise and wanted a margin of error of only 0.02 or 2%, what would we have to do? As we discussed earlier, we would need to increase our sample sizes significantly. This would decrease the standard error and, consequently, pull that margin of error down. This conceptual understanding is just as important as the calculation. Being able to explain typical variability versus confidence is what separates a good statistics student from a great one. As we wrap up our exploration of topic 3.10, it is important to know exactly when to reach for this specific tool. The two-sample z-interval for a difference between population proportions is very specific. Here is a checklist for using this procedure. First, you need two distinct populations or groups. Second, a categorical response variable, usually success or failure. And third, independent samples or a randomized experiment. If your data is quantitative, meaning you are looking at averages or means rather than proportions, you would use a t-interval instead of a z-interval. If you only have one group and are comparing it to a fixed number, you would use a one-sample procedure. Let's summarize the interval construction. The point estimate is p-hat 1 minus p-hat 2. The critical value is z star. The standard error is SE. Finally, the interval is the point estimate plus or minus the product of z star and the standard error. Let's do a final review to reach our goal of mastery. We learned that the standard error is the square root of the sum of the variances for each proportion. We also learned that the margin of error is the product of that standard error and our critical z-value. Before you finish, think about this. Why do we use p-hat in the standard error formula for a confidence interval, but in other tests we might use a pooled proportion? In a confidence interval, we are trying to estimate where the true proportions are, so we use the best information we have from each individual sample. We don't assume the proportions are equal, so we keep them separate. Let's recap our goals. Goal 3.10a, identify the procedure? Done. Goal 3.10b, verify conditions? Done. Goals 3.10c and d, calculate standard error, margin of error, and the interval. Done. You are now equipped to handle two sample proportion problems with confidence. Whether you are comparing city app usage, medical treatments, or state laws, the steps remain the same. Define your parameters, check your conditions, calculate your components, and interpret your results in context. Great job today! Keep practicing these calculations and interpretations, and you will be well prepared for any two-sample proportion question that comes your way.